Welcome to our latest explainer. Today, we're tackling what is essentially the ultimate biography, the complete life story of the universe itself. We're going to trace the grand cosmic timeline, starting from the chaotic, fiery birth of literally everything we know, all the way to its distant, unavoidable end. It's an incredible story full of mind-bending physics, scales that are almost impossible to imagine, and some deeply fascinating mysteries. Let's dive in.
So, how exactly does a universe die? It's this massive existential question humanity has pondered for thousands of years. I mean, will it be fire and brimstone, or something a whole lot more chilling? Well, here's the thing. To truly grasp how it all ends, we first have to look at how it began. The clues to our ultimate cosmic fate are actually buried deep in the ashes of the Big Bang.
Part 1. The universe's glowing echo. To understand our ending, we're rewinding the clock 13.8 billion years. Back then, the cosmos was basically just a dense, opaque fog of unbelievably hot plasma. But as the early universe expanded, that plasma cooled, the fog finally lifted, and a massive burst of light was released into space. Today, we call this the cosmic microwave background, or CMB. It was actually discovered completely by accident in 1964 by radio astronomers Arno Penzias and Robert Wilson. And this relic radiation is essentially the ultimate proof of the Big Bang. It's the universe's oldest baby picture, and it literally fills all of observable space.
Just think for a second about how much the universe has changed since that explosive birth. 2.725 Kelvin. That is the literal temperature of this cosmic echo right now, today. To put that into perspective, that is just a tiny fraction of a degree above absolute zero. The intense, blinding heat of the Big Bang has been stretched out and cooled down by the expansion of the universe over billions of years, settling into this freezing, faint microwave glow.
And here is a staggering thought. Without that relentless cosmic expansion cooling the CMB down, the energy density of this relic radiation would be so intense that your night sky wouldn't be dark at all. It would shine as brightly as the sun. It's wild because it connects this highly abstract physics right back to your everyday reality. The only reason we even have a dark night sky is because space itself is stretching out and cooling down.
And just to really hammer home how dominant this primordial light is, 400 to 1. For every single photon of light ever emitted by every star and every galaxy throughout the entire history of the universe, there are 400 ancient CMB photons. The light from the Big Bang outnumbers all the starlight in the cosmos by an absolute landslide.
Section 2. Cosmic Fast Bloomers.
Fast-forwarding slightly from the baby universe right into its teenage years, the James Webb Space Telescope is completely revolutionizing our view of early galaxy formation. Now, you might have seen some of those wild clickbait headlines recently claiming, JWST broke the Big Bang, or that it found galaxies older than the universe itself. While the reality, JWST didn't break the Big Bang at all. The 13.8 billion-year-old age of the cosmos remains perfectly intact. What Webb actually proved is that early galaxies were just cosmic overachievers. They matured incredibly quickly.
Let's look at a specific example to make sense of this. Meet MOMZ14. We're observing this galaxy as it existed just 280 million years after the Big Bang. Now, in the grand scheme of a 13.8 billion-year-old universe, 280 million years is a literal blink of an eye. Yet this compact dwarf galaxy had already pumped out 100 million solar masses worth of stars. It was highly luminous, highly efficient, and it turned its available gas into stars way, way faster than any of our standard models predicted. The secret to these early galaxies is a phenomenon astronomers like to call mini-quenching. Think of it kind of like a cosmic growth spurt. Starting from the Big Bang at year 0, a galaxy might hit the 300 million year mark and suddenly experience this violent, intense burst of star formation. But then, just tens of millions of years later, it totally stops. The star formation shuts down, or quenches. It doesn't slowly build up over billions of years like our own Milky Way. It blooms incredibly fast and then goes totally quiet.
To quote the researchers directly here, a spectral sign of maturity can instead be the aftermath of a rapid burst. See, when astronomers point a telescope and see a mature or quiet galaxy full of red stars, we naturally assume it must have aged slowly over billions of years. But in the early universe, that red, quiet appearance just means it burned extremely bright, exhausted or blew away all its gas, and shut down fast.
Section 3. The ultimate cosmic fate.
Okay, so now that we've seen the chaotic, rapid-fire youth of the cosmos, let's push the narrative forward into deep time and look at our ultimate fate. To understand how it all ends, we really just need to look at the ingredients of our universe. Everything you've ever seen, touched, or interacted with, every star, every planet, you, me, makes up a tiny 5% slice of normal matter. Another 26% is invisible, dark matter. But that massive 69% majority, that's dark energy. And because it's the biggest piece of the pie, it dictates our future. It's a mysterious force pushing space apart, basically ensuring that our universe will expand forever.
Discovering this fate has basically been a century-long detective story. Back in the 1920s, Alexander Friedman's math proved the universe couldn't be static. It had to be expanding or contracting. By the 60s and 70s, astronomers added up all the mass they could find and figured gravity would eventually win, predicting a dramatic collapse. But then, in the late 1990s, scientists studying distant dying stars, supernova, found something completely expectation-defying. The universe wasn't slowing down to collapse. The expansion was actually accelerating. Dark energy had officially entered the chat.
The contrast between those old theories and our current reality is pretty stark. For decades, we pictured the big crunch. Gravity overpowers expansion, and the universe collapses backward into an infinitely dense point. Basically the Big Bang in reverse. It's a visually appealing, almost poetic idea of a cosmic cycle. But the dark energy-driven reality is much more chilling. The Big Freeze. Dark energy accelerates the expansion indefinitely, meaning the universe is just going to keep ballooning outward until all heat and light simply fade away.
Let's walk through these haunting final steps into what astronomers call the dark era. First, trillions of years from now, galaxies will drift so far apart that the night sky outside our local group will just be pitch black. Next, as all gas is locked up or exhausted, star formation will permanently cease. The remaining stars will just die out. Fast forward about a Google years, that's a 1 followed by 100 zeros, and even the supermassive black holes will evaporate away via Hawking radiation. Finally, the universe's temperature will settle just a smidge above absolute zero, maximum entropy, empty and completely dark. Which leaves us with this final, truly profound thought. If our universe is ultimately destined for a big freeze, an eternity of cold, empty darkness, what does it mean that we are here, right now, to see the light? We exist in this incredibly brief, beautiful window where stars are burning, galaxies are shining, and the universe is warm enough to support life that can actually look up and figure it all out. What you should take away from this isn't existential dread, but a deep awe for our present moment. Thanks for joining me on this journey through the cosmos. Keep looking up, and I'll catch you in the next explainer.